Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video, I'm going to talk about how to find equivalent circuits for AC circuits. We will do an example. Recall the process of how we find equivalent circuits. First, we find the open circuit voltage. Next, we find the short circuit current. And last, we take the ratio of the voltage to the current, and that is the Thevenin's equivalent impedance. Of course, the open circuit voltage is the Thevenin's voltage, and the short circuit current is the Norton's current. That, together with the impedance, gives us two equivalent circuits, the Norton equivalent circuit and the Thevenin's equivalent circuit. Consider an example. Here's a circuit with an independent voltage source and an independent current source, along with an inductor, a capacitor, and a couple of resistors. And in this problem, we want to find the equivalent circuit seen by the capacitor C. So here are some values for the components. The two resistors are both 8 ohms, the capacitor is 5 microfarads, and the inductor is 3 microhenries. And I'm also giving you the input voltage, V of t, is equal to the cosine of 300 t volts. And the current, I of t, is 2 cosine of 300 t amps. One thing I do want you to notice is that in both of these sources, omega is 300. That's required. In a AC circuit, you will have a single omega for the whole circuit. So that must be the case. Okay, so I want you to find the equivalent circuit seen by this capacitor. We're going to do it the same way we've done it before. We're going to find the open circuit voltage and the short circuit current. And then we'll take the ratio of those two. So let's start by finding the open circuit voltage. Here's the circuit again. I've gone ahead and labeled these node voltages V1 and V2. And I wrote in that V of t is cosine of 300t and I of t is 2 cosine of 300t. Okay, so the open circuit voltage is going to be the voltage if we remove, let me go ahead and I'm going to sketch it in. If we remove the capacitor, okay, if we remove that capacitor, that is the open circuit voltage, VOC, and that is V1, okay? So we'll just write that down, note that VOC is equal to V1. Now I'm going to go ahead and write my equations. I'm going to do nodal analysis. Before I start, I want to point out that if we wrote V as a phasor, it would be 1 at an angle of 0 degrees. And if I write I as a phasor, it will be 2 at an angle of 0 degrees. And I'm going to do that so that I can go ahead and just plug it in as I go. Often I will keep values that are variables, but this time let's go ahead and plug them in. So as we go, we have at this node, we're going to have a current leaving here and a current leaving here. And of course, this is an open circuit, so there is no current leaving. So we'll say V1 minus, this node is called V, so V1 minus V over 8 plus V1 minus V2 over 3 microhenries. So that's 3 times 10 to the minus 6. And we want to do the impedance, right? So it'll be J omega L. So there's J omega is 300. Let me go ahead. I must have a little space. J times omega, which is 300, times L, which is 3 microhenries. And that will be equal to 0. Okay, so let's go over that again. We have V1 minus V over 8 plus V1 minus V2 over the impedance, J omega L. So J, 300, 3 times 10 to the minus 6. And this current is, of course, 0. So those sum to 0. In V2, we can write a similar equation. So we'll have a current leaving here, V2 minus V1 over the impedance. current leaving here, V2 minus 0 over 8, and we'll have a current entering here. So let's write that down. We have V2 minus V1 over J omega L, which is 3 times 10 to the minus 6, plus V2 minus 0 over 8. And then we have a current entering, and that current is going to be entering, so it's negative, and it's going to be 2 at an angle of 0. And I'm going to go ahead and write it as a phasor right now, but you'll see in a moment that that becomes just the value of 2, minus 2. Okay, also at this point, we can go in and substitute in for V. I probably should have done that to begin with. V, of course, is 1 at an angle of 0, so I'll go ahead and leave that in as well. So this is the step I kind of do when I finish writing my equations. I remember I double check and make sure I put in all my unknowns and put in all my knowns and have my impedances correct. And so what I can see is that I have 2 unknowns, V1 and V2, and 2 equations. So I can then remember, I'm just going to put a note here. 1 at an angle of 0 degrees is equal to 1 plus J0, which is just 1. And 2 at an angle of 0 degrees is 2 plus J0, which is just plain old 2. So when we plug all these values in, we'll have V1 minus 1 over 8, V1 minus V2 over an imaginary number. And the same thing over here, V2 minus V1 over an imaginary number plus V2 over a real number minus, and this will be 2. Okay, so now we just need to do, simplify those equations. Here they are written again, a little bit more clearly perhaps. And what we're going to solve for, of course we have to solve for V2 and V1. Well, I guess it kind of comes with most solutions. But what we really care about is, of course, V1, and that's VOC. Now, one thing I want you to note is that we can write this in the form of a matrix. So we have something times V1, V2, and that will be equal to something. Okay, so they have values in here. And so that's going to give us something times V1 plus something times V2 will be equal to that value over there. Same thing, this times V1 plus this times V2 is equal to this value. So if we take these equations and write it in matrix form, it becomes very simple to plug into MATLAB. Okay, again, on your calculators, you probably have to do most of the work yourself because most calculators do not have the ability to solve a matrix system of equations with complex numbers, but you can go ahead and type into MATLAB to check yourself, which is always a good thing. On tests, of course, you don't have that option. Okay, so when I take these 2 equations and I write them in matrix form, this is what I end up with. Okay. When I put that into MATLAB and solve, I end up with V1 is equal to 8.5 at an angle of 0 degrees volts. Okay, V2, you also find what that is, but it doesn't matter for our purposes. So we can take this value and write it as a times value. VOC of t will be 8.5 cosine omega t volts, where omega, of course, is still 300. And that is our Thevenin voltage VT. The next step, of course, is to find the short circuit current. And in these notes, just an aside, in these notes, I do have the MATLAB code for doing that solution so that you can use that as a model for when you're checking your answers. Okay, now let's find I short circuit so that we know I Norton, and then we can also calculate Z Thevenin. Okay, so if we're going to short circuit, the capacitor, we're going to replace that capacitor with a wire, okay? And what that is going to mean is that V1 will now be equal to 0. Okay, it's kind of odd looking, but it's going to work if you just work the problem. So we need to know what I short circuit is. So now let's go ahead and find I short circuit. Let's write a nodal equation at V2. And the reason I'm going to choose to do that is when I look at V1, it looks a little odd. So I'm just going to start with the easy one first. And I'll get V2 minus V1 over the impedance of the inductor plus V2 minus 0 over 8 ohms minus 2 at an angle of 0 degrees will equal to 0. So let's write that down again. V2 minus V1 over j omega L, so j omega is 300, and L is 3 times 10 to the minus 6. So that's that current. This current will be V2 minus 0 over 8. And then that will be an entering current 2 at an angle of 0 degrees. Okay, one thing we notice at this point is that V1 is equal to 0. So let's go ahead and put a 0 in for that. Okay, so V1 is equal to 0 because we tied it to ground. So now we have V2 minus 0 over a complex number plus V2 over a real number minus 2 is equal to 0. When we solve for it, we can solve for V2. Okay, and then we'll do that in just a minute, but then we will also have to find I short circuit. Let's go ahead and write that equation. We'll say V1 minus V, which is 1 at an angle of 0. So V1 minus V over 8 plus I short circuit leaving plus V1 minus V2 over that impedance, so plus V1 minus V2 over J, omega is 300, L is 3 times 10 to the minus 6, will be equal to 0. Okay, so let's talk through this for a moment. V1 is 0, so we can replace this with 0. And of course, feel free to copy your equations over. I just do it as I go. So when we look at this, these two equations, in the top equation, we can solve for V2. In the bottom equation, once we know V2, we can solve for I short circuit, which is what we're looking for. So when we plug in the numbers and solve, we have our equation from the top. When you simplify it, you end up with this. Okay, and then we take 2 and divide it by 0.125 minus j 1111.1, and we will end up with V2 is equal to 0 plus j times 0.0018. So it's going to be a mostly imaginary number. So this just is so small that it looks like 0. Relative to the other value. Okay, so now, and you could try that on your calculator at home. So now we take the value we have for V2, we plug it into our equation, and we solve, and we end up with I short circuit is 2.125 plus J0, and that will be our Norton current. Okay, in both these cases, we can write both the cases. So we already wrote V of t, so now we can write In of t. It'll just be equal to 2.125 cosine omega t. And omega, of course, is 300, and it's amps. To find the impedance, we divide the VOC by I short circuit. This one's kind of simple because what we have is V of t, let me go back to it. V of t is equal to 8.5 at an angle of 0. And I of n is 2.125 at an angle of 0. So I did not write in the angle of 0 here, but you could have if you like. But what that's going to be is 8.5 over 2.125, which turns out to be 4 ohms. And so we end up with a interesting situation where ZT is purely real, and so it is a resistor without a capacitor or an inductor. I hope you found this helpful. Thanks for watching.